Okay, so we talked about this a little bit. We just mentioned a little bit more detail about it. Ionic bonding. So if I make a compound is formed by bonding elements together. There are two types of bonding. One type is covalent bonding, which we'll talk much more about next week. Covalent bonding involves a situation where pairs of electrons are shared between atoms. We'll talk much more about that later. Ionic bonding is much more simple. Ionic bonding, as we said, just is forming a bond between atoms if they have charges and they have the opposite charge and those opposite charges attract. So why do they have charges? To make the same number of electrons as a noble gas. If they have opposite charges, why do they attract? Because opposite charges attract. That's a bond. That's an ionic bond. It's really that simple. When they come together, though, the only complicated thing about that really is that the formula that results has to be neutral overall. So I have to have a number of positives and negatives that balance out if I'm going to make that my unit. That's my formula that tells me what all the other units should look like that are repeating in that sample for the sample to be stable. How do the ions usually arrange? Well, they usually arrange in some type of cubic crystalline lattice. So crystalline means organized. Lattice also means organized. But the term lattice just refers to the specific arrangement. It also refers to maybe how close together they can get in that organization. And then there's also a lattice energy associated with that. Lattice energy is like ionization energy, except it's a little bit different, right? Ionization energy is the energy that you have to put in to overcome an attraction between the outer electron and knock it out of the atom. Here, the lattice energy is the energy required to overcome all these attractions. So if I have a bunch of these atoms, lattice energy is usually given in per mole, and a mole is just a number of atoms. So if I had a mole of these units of NaCl in the solid state, that means I've got Avogadro's number of them, or just a huge number of these units all packed together. How much energy does it take to break those up? A lot. If I have a huge number of positives and negatives all lined up and I want to separate them from one another and get them as individuals, it's going to take a lot of energy. And so that's what the lattice energy represents. The positive value because it's energy I have to put in to overcome that attraction. So when I'm making an ionic compound, if there are salt mines under Lake Erie, with these ionic compounds that are already formed, right? So the point to this activity, not really an activity, we don't have a lot of time to really give you a chance to think about it, but the reason this is on here is because, again, when I'm going to form an ionic compound, usually it's taught as a transfer of electrons. But I'm trying to impress upon you the idea that these ions are already found with charges, naturally. They don't have to meet to exchange electrons. Right? So in nature, if I want to make an ionic bond between an Na and a Cl, I don't have to take an Na with 1 valence electron and add it to a Cl with 7 valence electrons and get the Na to transfer its electron over in order to make NaCl salt. That doesn't really happen because Na does not exist in nature with 1 valence electron. It exists in nature without already having a positive. And the chlorine doesn't exist like this. There's no chlorine gas. You don't have to walk out of your house and worry about getting hit by a cloud of chlorine gas. Chlorine already exists with a negative charge, which is stabilizing for it. So if you run into chlorine salt with a negative charge, it doesn't do damage to you because it's stable. It's not ripping electrons off your body like a chlorine gas would to grab the electrons it needs to make the same number as a noble gas. So since these are already found in the form of ions, they don't have to actually transfer electrons. They're already charged. All they do is allow their attractions to cause them to organize into a crystalline or organized three-dimensional shape if it's going to form a solid.
If chlorine were to rip your body, would that be chlorine with the carbon, component-wise?
No, just chlorine. It's just chlorine atoms.
Okay.
Yeah, not chlorine gas.
Or carbon, that kind of thing.
It's just pulling electrons. So you're made out of carbon atoms that have electrons around them, and those electrons are used to connect those carbon atoms to other carbon atoms and to oxygen and other things. the chlorine would be pulling those electrons out. And so the molecules that make you up are able to stick together the way they normally do if their electrons start getting pulled out of them. So one other quick point here is that you may or may not be aware, but sodium metal explodes when you put it in water. Why is that? So water is pretty stable, right? We don't usually think of water as being explosive. Water has this Lewis structure. So when I show a line between atoms, that is the situation where the two atoms are sharing electrons. This is the structure for water. The oxygen has 8 electrons around it, which is the same number as neon. But if I put sodium metal, not sodium ions, if I have sodium ions, that's already stable. Nothing's going to happen if I put that in water. It will just mix it with the water and they would be happy. But if I put a sodium atom, a neutral sodium atom, sodium metal, which doesn't exist in nature, I have to make that in the lab if I want to get it. But if I do, and then I take a chunk of it and put it in water, what would I expect to happen? On a molecular scale between the individual atoms, what do I expect to happen? What does the sodium want to do? Does it want to add more electrons? No, it wants to give up its electron. It will give up its electron to anything that's around. This electron will go onto the water. An explosion is a release of a lot of energy in a short period of time. So when I put that sodium in water, all the atoms on the surface of the chunk of sodium have this one electron that they want to get rid of to make the same number as the noble gas. And so in a very short period of time, very many of those atoms will lose that electron and the water will pick it up. What attracts an electron better, the sodium or the oxygen? The oxygen, right? The oxygen is smaller. The electron can get close to its nucleus in that second energy level. So I have a situation where the electron is not very stable because it's in the third energy level of the sodium, and there's a lot of shielding. And if that electron leaves that area and gets close to the oxygen nucleus, it's going to be a lot more stable. It starts off unstable, high in potential energy, moves to a stable position, low in potential energy. And if I have a high potential energy and go to a low potential energy, a lot of energy is released in a very short period of time. That's what an explosion is. If I have a high potential energy situation and I go to a low potential energy situation, that energy is released over a long period of time. It's just slowly heating the environment. It's not going to be an explosive situation. So about the lattice energy then, what we're saying was when these ions are organized, their positives and negative charges are what keeps it together, right? So I've got the sodiums in white here, they're all surrounded by chlorines. My chlorines are all surrounded by sodiums, right? They organize in a way to maximize those charges. So if I want to quantify the lattice energy, I can do that experimentally. Or I can use this formula that we already saw earlier in the semester where we saw charged particles attracting. When charged particles attract, the quantity of charge and the distance between them are the main factors that affect how much they attract. So the more charge they have, the more they attract. That also goes for ions that are organized in this three-dimensional structure. And the closer they can get, the more they attract. So just to see some examples of that. So I've got a variety of metal ions with the iodide. Right, so the metal ions have a +1, the iodide has a -1. So the amount of charge on top of this fraction is the same for each one of these. The difference is, since the lithium is smaller, because it has fewer levels, I can pack things closer in there. They can get closer to one another. The charges get closer. When I think about this, I've got like gaps in here because these are both large atoms. If I want to pack things tightly and get a stronger attraction, a greater lattice energy or a stronger attraction between the ions, the smaller this one is, the more I can pack it in next to the other one without creating gaps between them. So the lattice energy is somewhat affected by the size of the atoms and how closely they can pack into an ionic solid but it's more affected by the quantity of charge. Right, so in this situation, if we're looking at something with one positive and one negative, then the attraction between them is on the order of about 1,000 kilojoules required to break up that attraction. But if I put more charge, and my ions have a +2, or my ions have a +3 and a -3, then I get way more energy required to break up those attractions. So the primary factor affecting the melting point of an ionic solid and how strongly the ions are held together in an ionic solid is how much charge the ions have. A secondary factor is how closely they can pack in when that organized crystalline structure forms. There are a variety of tables in your textbook that show a variety of ions, and that's not something you need to memorize. I mean, most of these you can just figure out by looking at where the elements are in relation to the noble gases and see whether they need to pick up electrons or lose electrons to make the same number as the noble gas. And so then the last thing that we need to finish up here is how do you create the formula, and this is exactly what the example was that we went over in the beginning. To create the formula, you need to make sure that first you determine what the charges should be on the individual atoms, and then you create a formula with the number of each element that you need to keep the charge overall balanced. Must equal 0 for the overall charge. Right, so if I have aluminum ions, I find aluminum on the periodic table. It's right here. To make the noble gas configuration, it needs to go from 13 to 10. It needs to lose 3 electrons. So that means I'm starting with aluminum 3+. Oxygen ions are 2 away from a noble gas, but they need to pick up 2 electrons. So if I'm doing that, they will have a 2-. So then I just need to organize these in a way that gives me a formula. So a quick shortcut to doing that is to take the charge of one and make it the subscript for the other atom. And then I take the charge of this atom and make it the subscript for the opposite atom. That gives you a situation where I have 2 aluminums. Right, the 2 here means that's a number of aluminums, and I have 3 oxygens. So 2 times a +3 and 3 times a -2. That gives me a total of -6 and a total of +6, and that all cancels out to give me 0. Another way just to think about that is to say, well, if the ratio were 1 to 1, the charge would not be balanced. So what do I need more of? The one that I start with less. So I would add another oxygen. Still not balanced. Now I have too much negative, so I add a positive. Still not balanced, so now I have too much positive, so I add a negative. If I do it that way, eventually I'll get to the point where the quantity of positive and the quantity of negative is equal. And so I can say I have 2 aluminums and 3 oxygens, and that gives me a balanced formula. Any questions about that? In order to make this type of structure, which is the way ionic salts will exist, I need in each repeating unit, I need the overall charge to be 0.